Bismillahirrahmanirrahim. Today is our lecture number 21st, and we have started the definition of split. So we have started the definition. Definition: a short exact sequence like this. Yesterday in last three lectures we are also studied what is short exact sequence. So this is short exact sequence. This short exact sequence is said to be split if and only if image of f is the direct summand of b. Before study the definition, this definition, I have revised some definitions to you. So we have go to last lecture. In this theorem, yesterday we have studied image is a direct summand of b. So we have write b is equal to kernel of alpha. For direct sum we have used this symbol, addition under circle, and image of f. So this is a definition of direct sum. We have come to the definition: short exact sequence O to A and a function f defined from A to B and a function g defined from B to C. And C goes to again O. This sequence is short exact sequence. This short exact sequence is said to be split if and only if image of f is direct summand of B. After this, we have studied corollary. This is a well-known corollary. A short exact sequence O to A if as a function defined between A to B and G is a function defined B to C and C approach to O is split if and only if there exists a homomorphism alpha from B to A such that alpha composition F is equal to identity. Yesterday we have also studied basically if alpha from B to A, alpha is the inverse of F. Basically F is defined from A to B. See the head of the arrow. Basically arrow goes from A to B and function is defined. This means that function f is defined from A to B. But alpha, in the instance of alpha, the head of the arrow goes from A to side of B. So basically alpha is the inverse of f. So this corollary states that if we are considered the short exact sequence, then this sequence is split if and only if there exists a homomorphism. Homomorphism is basically from alpha from B to A, which is the inverse of f, such that the composition of those functions will be identity. For homomorphism, I have revised the definition of homomorphism. Basically, we are taking two modules, m and n. So a function f from m to n is said to be homomorphism if let's satisfy the following condition. Number first, we are taking two elements m1 m2 belong to m such that f of m1 plus m2 is equal to f of m1 plus f of m2. Condition number second, we are taking one element from ring R belong to ring and m belong to m, then f of Rn is equal to R f of m. So this is the definition of homomorphism. This theorem is very simple. Yesterday we have also studied this theorem. So you should try to prove this. If you want to feel difficulty, you should contact with me. After this, we are studying another corollary. In last corollary, in a previous corollary, in this corollary, we are studying the inverse function. Alpha is basically inverse function of f. So alpha is defined from B to A. But in next theorem corollary, we have studied like beta from C to B. So let's start the statement of this corollary. A short exact sequence O to A and A to B if is a function defined between A to B and G is a function defined B to C and C approach to O is split if there exists a homomorphism beta from C to B. Before I have revised, basically in last corollary we have defined there exists a homomorphism alpha from B to A. and prove that alpha composition F is identity. But here in this corollary we have studied beta. There exists a homomorphism beta from C to B such that G composition beta is identity. So this is also very simple. You should try. After this, we have studied another corollary. A short exact sequence O to A, and F is a function from A to B, and G is a function from B to C, and C equal to 0 is split. This is basically short exact sequence. Is split if there exists a homomorphism beta from C to B such that B is equal to F of A plus beta of C. F of A is mean we are taking F of A is basically a set which contain like such kind of element. We are taking element A belong to A and assign to a function F. This the result of F of A will be belonging to B. So basically F of A containing B. And beta of C. So beta of C, beta is a function basically defined from C to B. So beta of C, we are taking element from here assigned to beta of function B. So the result will be here. So when we are add those sets, the result will be B. So this is very obvious. After this, we have studied again a definition. This definition states that a short exact sequence this is said to be split on the right number first right if and only if we are consider this sequence. This is basically a short exact sequence is said to be right split if we are consider this B to C to O, and it is left if we are consider this 0 A to B. So this definition states that a split is said to be from here a short exact sequence O to A, A to B, B to C, and C to O, and they contain two functions F and G. F is defined between A to B and G defined between B to C. This sequence is said to be split on the right, if and only if we consider this upward from B, and if we say that this will be left if we are consider before B, like OAB. So this is the definition of right split, left split. After this is very well known result. This is very important result. And this theorem states that let O approaches to A and F is a function defined from A to B, G is a function defined from B to C, and C approaches to 0. Approaches mean that this we are defined that basically, for example, here we stated B approaches to C. So here is a function G, which is particular function which is defined from B to C, but here he will not mention which kind of function defined from C to O. Be in exact sequence of our module and there are homomorphism, then the following are equivalent. So for this, number first, the sequence splits on the right. Number second, the sequence splits on the left. Number third, image of F equal to kernel of G is direct summand of B. So we have considered the sequence split on the right. We proved that number third. About this, since it is assumed that a sequence split on the right, so there exists R homomorphic beta from C to B such that G composition beta is equal to. This is basically we have used a corollary. Which one? Let's see. Basically this. We have used this corollary. Beta from C to B, G composition beta is equal to identity. So by using this corollary, let X belong to B. X belong to B. Let's mean that G of X, we have also write G of X minus X, but here we have write identity. So instead of identity, we have write what? Beta composition G. So we have apply what? Basically, we are taking element from here. X belong to B and assign to what? G, the function G. So basically, we are taking X belong to B and G of X minus X. We have write because there is no element, so we have write X minus X. So X minus X, but we are also write X is equal to 1 dot X. So instead of 1, we have write G composition beta or beta composition G. After this, we have applied this function. So G of X minus G of beta composition G of X. After this, we are applying composition of function. So associated composition of function. After this, we are again applying composition of function associated law. After this, instead of this, we have write identity in composition of G of X. After this, G of X minus G of X is equal to 0. That means that X minus this element should belong to kernel of G, because when we are taking element from a kernel of function, then the element should be under function value. When we are assign these elements which are taken from a kernel of G, we are assigned to a function G. The result will be identity. After this, X is equal to beta composition G of X plus X minus beta composition G of X. So basically, we have solved this under G, but this we have count, because we have write X is equal to X plus this and minus this, because we have crossed to each other. Result will be again X. After this, beta, we have reopened the composition of function. So beta into G of X plus beta composition of G of X will belong to image of B. So this element will belong to image of B, because this contain this element belonging to image of B. Image of B contain those elements which we are taken from a set assigned to beta. The result will be in another set. And this element we have already proved that here belonging to kernel of G. So after this, B is equal to image of B plus kernel of B. After this, we have proved that direct sum. For direct sum, we have also proved that the intersection will be empty. So we are taking X belong to image of beta intersection kernel of G. That means that intersection may contain those elements which belong to both sets. So that means that X is belonging to this and also belonging to kernel of G. X belong to image of B. That means that X contain like beta of C kind of element. And X belong to G of X. That means that G of X is equal to 0. And instead of X, we are put B of C. So again, we apply composition, and this is equal to identity. So identity of C is equal to again C. X is equal to BC, B of 0. And then again, the result will be 0, because we have already put this mean X is equal to B of C. So we have write X is equal to B of C. We already proved that 0 is equal to C. So from here, we have put this value of C is equal to 0. The result will be again 0. So this set intersection will be 0. We are taking arbitrary element and it is equal to 0. So the intersection of both will be 0. So we show that beta is equal to image of B plus kernel of G. After this, we have assumed that the second part. After this, we have show that number second from right spectrum proof that this is very simple. Similar here we have right left, and so right or left you have replace the elements. So the other proof section will be easy. You have tried to prove it. If you feel any complications, then you should contact with me. But this is nothing. This is very simple. This is nothing. The proof is very short. So you should try to prove this. If you feel any complications, then you will contact with me. Inshallah, we will study Lemma 3. So we have studied only the diagram of the Lemma 3. Basically, F is a function from A to B. A, B, C, M, N, P, Q. These all are modules. So F is a function from A to B. Alpha is a function from A to M. Which is a function from M to N. Beta is a function from B to N. This K is also function. G is also alpha is also function. These are sequences. Are also some exact sequences. So we have to with the following conditions. So inshallah, we will study in tomorrow lecture. Inshallah, we will note in next lecture if you have feel any complications or any difficulties in this lecture. So you should contact with me. Inshallah, we will meet in next lecture. Allah Hafiz.